أبدأ okay? Okay. So again, Assalamu alaikum everyone. So today's lecture will be about the occupancy grid, localization, mapping, and navigation using this robot, AgileX. Okay. So this will be the content of today. By the way, it's a long content, but each concept just have one slide, so we'll be very quick with the presentation. So let's begin by occupancy grid map. I believe you already heard about this from Dr. Rami's lecture. So simply, this is instead of we having a continuous environment, so we discrete this. So we discretize this map into occupied cells and free cells and unknown cells. So if you have like walls, but your field of view is only 3 meters, and this wall is on 4 meters from you. So you have 3 meters. That's white. That's free. Maybe the figure is not clear, but this should be like this. This is white, okay, and this wall should be black. But you already you're not sure it's black or not because it's out of your field of view. So on these 3 meters it will be gray. You don't have any knowledge like this. Then if you approach the wall, if you approach like 1 meter or 2 meter, so you have this wall. You are sure now it's black. It's occupied, okay. So you will have this map instead of being like map with obstacles or something. So this is like a binary map in order to comprehend this map for ROS. Okay. So the other concept is LiDAR. What is LiDAR? This is a LiDAR, by the way. This is RoboSense LiDAR. So as Dr. Rami said in the previous lecture, it's like a sensor that emit light beams, thousands of light beams continuously in a rotation with a servo inside. It emits light beams, and these light beams, when it hit the wall, it reflects back to the sensor. So it reads with the calculation of speed of light and time and this stuff. So it calculates the distance. So it knows that this is wall, this is free, something like this. Okay, and if you remember, Dr. Rami also said, shows a picture of ultrasonic sensors that you can replace this LiDAR with multiple of ultrasonic sensors, and in the middle there is a servo that rotates these sensors. Okay, so this LiDAR is a 16 channel. What it means by 16 channel? That we can replace this LiDAR with 16 ultrasonic sensors. So it can rotate with a servo like this. Okay. Yeah, that's all about the LiDAR. Through the LiDAR also, we get the information like this occupancy grid map. We get this information from the LiDAR reading. This is only, we will build today the map and localization and navigation only with LiDAR. No need for the camera, no need for any other thing, okay? So, third concept, that the LiDAR now, the LiDAR, it gives us data like binary data. It's there's a wall or the light is reflected at 3 meters or 2 meters, something like this. But it's thousands of data. So how to extract this data out of the LiDAR? Just a second. Okay, so this LiDAR, let's introduce the concept of ROS, Robotic Operating System. What is ROS? If we are humans, okay? So we are talking. So if me and Muhammad talking about subject like economics, for example. So I am a human talking about a topic that's called economics, okay? And Muhammad receives my message, my words through the same topic, okay? So now the ROS is the same analogy. I am human. In ROS, it's a node. okay? And Muhammad, another node. So the topic itself, it is the same. It calls the topic as well, okay? So I am sending a message. In ROS, we are saying it's publishing a message. And Muhammad is receiving it, so Muhammad is subscribing to this message, to this topic. That's the message I conveyed, the Muhammad is subscribing to it, okay? So it's very simple. So now let's see that this LiDAR is a node. A node that what I want to hear from the LiDAR. I want the data, the distances, or the location of holes, the location that the light is bouncing back from, okay? So this LiDAR is publishing the data through scan, this topic, called /scan, /scan, okay? And what is the message that it publishes it? It will be this message. This is a type of the message. The type of it is laser scan, like we are talking about economics, okay? So what is the type of words I say about this topic, okay? Maybe let's introduce something other than economics. Let's introduce something like I'm talking about my position. So I can say that my X, Y, and Z is something, okay? Also, I can say that I am located 3 meters from a reference frame, like this. So these two are messages about the position, but they have two different types, okay? So this laser scan is a type of the message that the LiDAR is sending through the /scan. This is a topic, okay? So how to get this data? We said that already. If I open the LiDAR and see the terminal, so only the data will be binary numbers, or even it's not binary, but it's thousands of data. How can I comprehend this? I have to visualize it. So in order to visualize it, we are using simulator called RViz. This is RViz. Okay, so these are the red dots here are the reading of the LiDAR continuously. Okay, there are many ways to see the data, but RViz is the most comfortable one in order to comprehend this data, how it's visualized. Okay, the fourth topic will be how the ROS topics. We already said you already know now the nodes and topics. Okay. So how the data flow will be in order to achieve our goal. What is our goal today? Is moving this robot from a point to another and make a map and make a localization of the robot. So the robot now can know what is the environment around it. So we are building something like digital twin environment of this room on RViz. And also this robot will know its location in the environment and how to navigate from a point to another. Okay? So this will be the flow of the data. Let's start. We have the only sensor, the LiDAR, and the robot itself. Why the robot? Because if I have only the LiDAR in my hand, I have to move. So I'm simplifying many things. So let's see now, we have the standard case, we have a LiDAR on the robot, okay? So the LiDAR will emit or will publish a message on topic scan, okay? What else, what other topics we have? The robot itself. What we are waiting for from the robot? We are waiting, Position, okay. Position relative to what?
To the body frame. What is
Okay, yeah.
And velocity.
Okay.
What else?
We have this elbow robotic arm.
Yeah.
We have this camera. We have this LiDAR. What else we can get from it?
The position of the arm.
Okay. The frame transformation.
Like fire.
Yeah, exactly. What else?
Let's
go back to the velocity. How you can get the velocity?
Using IMUs. That's one. Maybe. Or from the wheels.
Yeah, exactly. From the wheels, the encoders. Yeah. So the data from the encoder, it's published on ODOM. This topic, ODOM. Okay. So now we know how much the incremental movement of the wheel. Okay. So now we are estimating the location of the robot. Okay. But still relative to nothing. We don't know the environment around us. Okay. We also have these two topics, TF and TF static. What it means, let's start with TF static. If we have this camera, it's fixed. So whenever the robot is moving, the transformation from the frame of the camera and the frame in the center of mass of the robot will be the same. The same distance, same angle, same everything. It's fixed. But if you are, so these data are published into TF static. Okay. We also have the arm. So if you are moving, and the arm itself, it's moving like with some pose. So the end effector now, it's changing. The frame of the end effector, it will be moved somehow. So the distance between the frame of the end effector and the frame of the COM of the robot will be changing. So it will be published into TF only. So the TF, the published the topic TF, is responsible for the dynamic transformation of the frames. Okay. So now we have 4 topics, and the messages inside them. So we will collect all these messages and integrating them to another node, another human, or another human making some calculation called SLAM. SLAM, what it stands for?
SLAM.
Yes.
Simultaneous.
Yes.
Localization and mapping.
Yes, exactly. Simultaneous localization and mapping. So this node will receive all these data. We have the LiDAR data, the odom from the wheels, and the transformation of the frames in order to make a map and also estimating the location. How we can do that? Let's imagine that I am human, I am in the desert, so I don't know where I am. If someone needs to help me and he asked me, where are you? I cannot define myself. I will tell I'm in the middle of the desert. Okay, so this node will define me. How? Let's say I will move, I will walk until I find a wall in this desert. Okay, I will walk until this wall. Then I will walk beside this wall until I somehow imagine that I am in a circle of walls inside the desert. But still, I don't know the diameter of this wall. So I can imagine the map, but there are many possible maps I can build because there are many diameters I can build. Okay? But in this case, this is not my case. In my case, I didn't calculate the number of steps. But in the case of the robot, it has already the information of number of steps from the odom because we have the reading of the encoder. So it stores the data coming from the encoder. So it can estimate the diameter of this circle. Okay? So now we can integrate building a map while localize the robot itself, while knowing the location of the robot. Then this information will go to other thing called AMCL. AMCL, this is Adaptive Monte Carlo Localization. I think they didn't do that. Yeah. Simply, this AMCL is another chance to be sure of the location of the robot inside this map. Now we have a map. We have a predefined map coming from the SLAM. So this MCL is another chance to make sure of the location of the robot with the extended Kalman filter. I know you took Kalman filter, but I don't know extended or not. Yeah, with the extended Kalman filter and another thing called particle filter. I think particle filter, isn't it? Yeah. So let's ignore this so far. Then we are now having the map and have the location exactly of the robot. So now we can define a goal. We can define a goal or a pose for the goal and move the robot. The robot itself can move from its location to this goal. Okay. There are some stuff here, but let's keep this until the end of the lecture. Okay. So now let's see the 1, 2, 3, 4. These four sensors: robot state, mapping, and localization. These four are explained. What I said in these 2 minutes ago. This is the explanation. This is the sum of it. And now we have a predefined map on RViz. We can put this on RViz. Okay. From the localization and mapping, we have a map. Okay. This will be clear with the experiment I will do. Then in the 5th step, the navigation. So now we have a navigation, put it on RViz. Then we have a live update from the LiDAR itself. Okay. this will be the live update. Like the LiDAR itself will detect the wall. It will be like these red dots, and if it matches the map, let's keep this to the experiment. It will be clear. Okay, so I think we can go now to the experiment. Okay. Okay, so the robot itself has Ubuntu and installed ROS. So I think you should go to the recording after the lecture. I think. Okay. Okay. So this robot simply it has this remote controller. So if I put this stick in the middle, this switch button in the middle, so we can move it. Okay. And if it's like this, it will not move. Okay. Let's now begin. Let's start. Like refresh your mind. So in order to build a map, what is the first thing from the sensors I need?
The data.
The data. From what? From which sensor?
From the LiDAR sensor.
The LiDAR.
Yes.
Very good. So let's see. So now, these are the data coming from the LiDAR. As I said, thousands of data. We cannot imagine how it is. We cannot understand. So we have to visualize it in a simulator called RViz. Yeah. Let's name this LiDAR. Okay, and here, nothing. Okay, so this will be the reading of the LiDAR currently. This is live update. If you see there are fluctuations in the red dots. Okay, so if anyone would like to move, or okay, you see here. Yeah, you see, Dr. Rami, I think, see, yeah.
This is just like
Okay, if we are moving outside, it should detect the door as well. Okay, now we are building the map actually. Now we are exploring the map. So we are building it. Okay. This is enough so far? Think this is enough?
yeah, I think
We almost have a closed map. Okay. So, where is it? Now we have to save this map. So I will run multiple commands just to save this map. Okay. Okay, the map is saved, so we don't need this. We don't need this RViz anymore. We already saved the map. Let's call this map saved. Now let's access this map. Yeah, by the way, let's see this. While we are saving the map, it saves two things. This PGM, it's like PNG, JPG, it's just a photo, okay, to visualize it, and the YAML file. The YAML file, it's a file including the parameters of the map, the dimensions of the map, and the dots where exactly, and this stuff, okay. So now we are trying to access this YAML file because we don't need the image. We need the YAML file to actually work with it, okay. 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 Now, what we should do? We have the map. We have what else?
The file where it's stored.
Yeah. This is the YAML file. We
Yeah.
have to visualize it in RViz. So what else we need? We will put the map in RViz. What else we need in order to navigate in the environment?
Localization. I'm not sure. I think we
Uh,
did it.
Yeah, localization. No. Yeah, localization. Now we have only a map. Now we have a map in my hand. What else I have to do? I have to access the LiDAR again to have a live update on the map.
Oh,
Okay.
so we say we navigate the map, we build the map, we write it.
Yeah.
Now we use the LiDAR to see how accurate it is. or-
Exactly. Yes. So let's open this. Somehow there are some errors. Okay. So this is a map. Now, this is the map, and the red things are the LiDAR live update. Okay. So I think it's not correct, isn't it?
No.
So we have to click on this to depose estimate, and this square, this blue square, is just a visualization for the robot. Let's put the robot itself in RViz. It was here it is. Okay, it's not working now, but I'll figure it out. We'll figure it out, inshallah. Let's estimate the position. Yes. What?
What's the software you are using?
This is Ubuntu, installed in it robotic operating system, ROS.
Okay.
Okay, and this is a simulation program. It's called RViz. In order to comprehend the data coming from the LiDAR, and put a map and put everything. You can hear also about something called Gazebo. It's like RViz as well. Both programs are in Ubuntu
So
in
basically you
ROS.
are using two softwares together?
Not two softwares. It's the big umbrella Ubuntu. This is the software. This is the operating system. Okay, including it, we are using. You can use RViz without ROS. You can use RViz is just a program.
Okay.
Okay, but we are using gross in order to communicate with this program. Okay. Okay, so now this should be the position. Let's estimate the position right. So we click on this 2D pose. Maybe it's like this, pointing like this. No.
I think the whole position, not the orientation is wrong, the position itself.
The position itself, it's wrong.
I think it's in the axis frame there.
Let's move. Let's see. Ooh. It should update somehow. It's maybe like this.
Can I tell you where we are? This is the door up there, so you can see.
Which one?
The door is,
This?
No, on the left.
Okay.
You
Here?
see the inclined line
Yeah.
in the middle?
This one?
Yes, so the door is up. Yes, this is where you are.
It's pointing like this.
Wait. Okay, so to the left. To the left.
To the
yes,
left?
Yes. Take me like that. Somewhere.
Yeah, you're right.
It's like calibration.
Yeah, exactly. We have, by the way, we have to do this step whenever. Okay, so this is now the location.
Okay, live.
Raw sensor there.
So then, okay. So this is now the map, and this is the reading of the LiDAR. So now we know the location. The robot itself can know its location and has its map as well. We can go to the navigation. Okay, we can navigate from a point to another now, just by setting a goal, like this. Setting maybe goal. Where?
Should be here.
Okay, let's put it here, but I don't think it will work. Let's put execute. Okay, if we execute the goal like this, it will not move. Why?
You still need
There are two things actually. Okay, so the first thing, that there is no path between them, between the point now of the robot and the goal. There is no path. If I put a goal, it should build a green path.
Yes.
Let's see if I put a goal like here, for example. If I put a goal here. Build it like this. Okay. Should make a green path. Here, execute. Okay, the first point is not valid. I don't know. But the second point, that we are communicating with it, we are moving the robot with this remote controller. So if I shut down this, so it should move with the ROS. So we cannot operate the robot with two controllers at the same time. Okay. Exactly. Yeah. So if you remember in the beginning, I told you that if all ticks are on the top, so we cannot move the robot. We should make this switch in the middle. So I make it like this, it should move.
Different behaviors.
Yeah, exactly. So let's put a goal here. Something wrong. this.
I think you need to move around so that you can better update about the green, the free space. Could you say something about the white and the gray areas?
That's what I will explain if it moves, but because it will be. I think it may be like this. Let's say if I put a goal here. Yeah, this is a green path.
Yeah, but it's not the same orientation. Yeah, it's the.
I think it displaced a bit.
Yeah. It's here, pointing this way.
Here.
Here, yeah, pointing this way.
This way.
So can we go a little bit down there because it's this orientation.
Yeah,
No.
a bit.
It's somewhere here. So just make this wall.
Yeah.
See what I mean?
Could we ask why this specific camera? Because we have one, it's like same as.
Oh, can you say something about the camera?
It's called depth camera, right?
There's depth camera, yeah.
Not just the camera. RGBD.
Yeah, RGBD, yeah. But what else? We can make a SLAM. We can make this simultaneous localization and mapping with the camera itself, with only the camera. But today we are making with the LiDAR. And in the end, hopefully, we can integrate them. In the end of today, I will show you a picture that integrates both the camera and the LiDAR as well. But I hope this error does not come in again. So let's put a goal like here. So it should move to the door a bit.
It should move in your place.
What?
It should move here.
Let's see. Let's see.
Be careful.
Yeah.
Yeah. So this builds not 4 kilograms or so.
Yeah.
Actually, I was moving yesterday. I was moving this table behind with the robot itself, so pushing the table. What? The applications. Okay, it can go in dangerous areas with this belt. It can go in sandy areas, mountain. It can climb mountain. If you see the little mountain between the gym and here, yeah, we actually have video that climbs the mountain. Yeah, it's not like the mobile robot, the normal mobile robot with the wheels. The wheels can wear or something, but this belt is efficient in this case.
Shall we start?
Yeah. So we have now this path. It's built from the exact location of the robot to the goal. Okay. So now if I put it like this, execute. One is plan. Get a new plan. Should move والله. Okay, let's explain this. Maybe there are some errors. Let's explain this. Why this green is curved like this? It's not just a straight line from this with the screen itself. I think. Why this green line is curved? Not like a straight, just a straight from pose to another. Why?
I think he took the motion of the robot to account, so it will
Maybe
Because
it
it's
can.
around it will-
Yeah, yeah,
Rotation, you mean?
but maybe it can rotate in its location, then take the straight path instead of moving like this.
Maybe the cost.
What
If
is
you-
cost?
If you take, I don't know how the path plan.
Yeah, yeah, but you are approaching the answer. Yeah.
If you take into account maybe the amount of either the distance you will
Okay.
take or the amount of battery you will consume.
Not like this. Not like this. Anyone has another answer?
Maybe the fastest way to just move on continuously.
But the fastest way is it's just a straight line.
Yeah, but you will take time to rotate. But
Mm.
you can take the move.
Valid answer, but it's not the answer.
Okay.
It has solution with the orientation of it. So how to don't hit the wall. Maybe if it's instant that if it take the straight path,
Okay.
it might hit the wall.
Yeah, exactly. Actually, the answer in the dark and bright areas. We already in the beginning we already discretized the map into three things: black, white, and gray. Okay, the black is obstacle, the white is free cells, and the gray not unknown. It's unexplored cells.
Unknown to the robot or
Unknown to the robot. Yeah, for us. But what are the dark and bright areas? Both of them. يعني, عليكم السلام ورحمة الله. The dark may include black and white cells as well. Why? What are these dark and what is this
The
white?
margin where you should be away from the wall.
Exactly. Exactly.
That's why it's
Yeah. Exactly. So the point that you can imagine that all of this robot we can enclose it into a cuboid, like dimension of 2 meters by 2 meters by 2 meters. Okay. So this robot should fit. This robot should go from here to this location. So we are building a cuboid around it. We are building a cuboid around the walls. Okay. So the robot can fit safely, can go to the goal. Okay. With this cuboid. So you see that there are some dark areas. These dark areas are around the obstacles. So if we put the goal inside these dark areas, it will not get a plan. So this plan is only in the white one. So this concept, what I said so far, this is the artificial potential field concept. Okay. So it's a potential field, negative and positive, attracting each other, negative and negative, positive, repulsive. Okay. So this is artificial potential field that the robot itself is negative, and the walls are negative, or the obstacles in general are negative. Okay, and the goal is positive. So now the robot will be attracted to the goal, but will be repulsed, or there is a repulsive force between it and the walls. So it should go away from the walls and also in the same time go to the goal. Okay, so this is the concept of it.
I think I know what's the problem. If we
Ah.
count the body limits or the boundaries of the body in the simulation,
Yeah,
because maybe it's inside the grey wall, that's why it's not moving.
maybe. Yeah. Let's rotate it in its location. Actually, now it should see this is. I feel all of these problems are coming from the wrong 2D pose estimate. I'm not sure.
Maybe.
Let's remove this goal.
Why do you guys think there is a problem in all of this matching? Why is it so difficult?
Because
Why it's not working?
Because we built the map before, so it's now trusting the map that they built rather than the current lab.
What is a map?
representation, whatever the environment.
Location of certain features, right?
Yeah. So it's a representation of what's around
With respect to what?
to the body, because that's where we take the map.
But that's the thing. A map is not with respect to a body. A map is always with respect to the global frame, right? If I give you a map to with respect to the whole world. It's not with respect to you.
This is taken from.
From satellite.
Yes.
Here is different. We're building that map. So what Tariq did in the beginning, so the one without the red information is only where how the objects, how all of these dots were with respect to some global frame.
Okay.
But we built it from information about the actual frame, the B frame, B with respect to S.
Okay.
You know, all of these transformations. Do we know B with respect to S correctly?
The transformation.
This is called the localization. If you want to know where the robot is with respect to the global place, you need to have a sensor that can tell you where it is. And on your phones and on your cars or outside, you have a GPS. It tells you where you are in the world. But here we don't have it. We don't have a GPS, and it's not working here.
So we have to do it out manually.
What? Would it work? Inside of the lab?
No. You're inside the building.
So indoor localization is a completely different story than outdoor localization.
GPS.
Sorry?
GPS.
GPS outside helps a lot. Helps with that, but as we said, even the GPS itself is not enough. You need to add stuff, as you know, the camel filter and blah blah blah.
Tariq,
Yes.
can we orient it like this because we have kind of accurate place for it?
I think I can put a goal here. I hope it will work.
So
But it's,
the
still.
conclusion is that if you have localization perfect, the map will be perfect.
Yeah.
But because of the localization is wrong, you're facing all of these issues now.
بس الفكرة انه مستحيل تحصل 100% لوكاليزيشن تكون الماب 100% صحيحة.
But this is very wrong.
So
This is the problem.
keep
This
it,
is very
keep it.
wrong. And what Tariq is doing,
Keep
Yeah.
it, just
because
because that's
his
where the
information. He's
original
telling me, I
place.
think the robot is like this.
Yes.
Muhammad
Here.
The robot is like this, not like that. He's looking like the robot is here, it's not there. So he's
It was this
actually
or
telling me the
oriented
correct position.
the other
Just
way?
leave this one there.
أنا في دكتور النظام
You
It should know by
you
itself.
have like
Should do the localization, should solve the localization so that it knows where it is.
just رجع مكانك. So when we have the original place, which is this one.
Yeah.
So just from where it starts.
It's not calibration. You need to have
Go back.
you need to combine more sensors.
Yeah. Then
To make your
Can I,
slam
try?
bigger.
Yeah, sure.
Maybe use the camera.
Just
This is
pointing it in direction.
You need more sensors.
Yeah.
Or change the algorithm itself. You need something.
But this is door, isn't it?
yes. So this is the door, as you can see.
Yeah. Yeah, right. Right. Yeah.
But the software,
I'll be there because
we
it's
work on the software.
if you come here, the
Yeah.
هاي دكتور
Okay, let's move like this.
Just let's make
Let's
it
put a goal here.
Okay, so
تقريبا
Yeah, there is a plan.
1000 ريال. ده رخيص.
ها؟
الربع الواحد ده
I think
It's
you should-
updating the plan
maybe
itself.
نعم.
Maybe if you disengage it, it's disengage the whole control.
Yeah, I already done this.
How many? How
Yeah,
many
3 ticks, but you cannot move with this. You only move with it in the
Yeah,
middle.
but maybe the other one keep it engaged. But
I tried it yesterday and
it
it was
works.
working. Yeah.
Why is not just trusting it to plan? Which that should be the case.
It will move. It will move on this green path. But I don't know why it's not moving now.
What is a published point?
Publish point is just for publishing the current pose of the robot. So it will publish this point to the topic called, I think, pose published, pose estimate, something like this. But it's not related to navigation, to the point, to the goal point. Bring up.
Maybe you wanted to show the camera. Or
I
do
think
you need,
here. Yeah, I will show the camera as well. I'm still in the navigation. Just a second. I feel
Maybe you can
this
skip it,
was
it's not working.
this was the case. Okay.
Next everything.
So let's put it here. All goals are completed. It should work.
Make the
Okay,
door
okay.
like so small, maybe.
No, there is not a problem, but the bring up of the actuators, we now have a plan as a software, but as a hardware, we have to bring up the actuators to be controlled from ROS.
Okay.
So I already got this, but there is a refuse in the connection. I don't know the connection refused.
Okay.
Don't know why.
Computer vision
None of this is
Okay.
computer vision. What
So-
Tarek will show you next is the computer vision. We're only using LiDAR.
Yeah.
The
So-
LiDAR is connected. Maybe Tarek can show you the flow chart of what is of the connection.
I will show you only the camera, the camera view inside RViz. Where it was it?
Maybe you need to close the navigation so that it doesn't move separately.
Oh, okay.
LiDAR.
But this is actually the RViz itself. Okay, let's open the camera. Okay, here. It goes here.
There's something with the frames.
There is something messy today. I don't know. Yesterday was heaven, actually.
On top.
The frame. Here you mean the markers or upward? Here?
This is map, are you correct? You want it to be map? Or world?
It should be world. It should be world, no. Let's add this. 0. Should be opened here. Because let's start from the beginning. Everything is messy now. Okay. Let's add this camera. Yeah.
Open the error, see what's the error. No, here. Status error.
Here. Connected trees.
There's no, that's a transformation, it's just missing.
If it changes this, it's already the world.
works.
Yeah, but I don't know. Okay. What I imagine that you should see both views of the camera itself and the LiDAR integrated. You through the camera. I don't know if I have an image for this. I think that was it yesterday. Yeah, that was it yesterday. While the camera was seeing this shelf, you see these gradient of colors, these red dots. These were the reading of the LiDAR itself inside the camera. So the camera can see through or vis. So you can integrate both of them. Okay, but that was yesterday.
يعني نفس الفكرة حتى اللي تطلع في المقاطع اللي مثلا face recognition مثلا في الشارع.
Yeah, exact. Like the video that Dr. Rami presenting to you, the last lecture after the quiz, the video that has cones in the map itself, and when you are moving with the camera, isn't the same? Can you remember it?
Yes.
Yeah.
And
So
he
this will be the same.
And he made the 3D object.
Yeah, exactly. Yeah. So this will be the same. Just except that we are not making the slam with the camera. So the slam with the camera will be just like the video that Dr. Rami presented to you. But this only fusing both readings from the camera and LiDAR. So it will be something like this. But currently this is the view only from the camera. So it's updated. Okay. Let's move again.
You build on top of it. So now this is connected to ROS. And now if you run any algorithm that you want with computer vision, you can run it on it and then you can get it connected. Okay. So now can you wrap us with the flow chart that you had?
Yeah.
So can you just tell them some of it and wrap up with
I'm displaying the PowerPoint online, and at the same time I have to connect with the robot through Wi-Fi. So I'm sorry for this. But, yes. There's a question? Okay, so this was the flow chart for those who didn't come early. We have the sensor, the LiDAR itself. This is the LiDAR. Okay, this is the sensor. This is the only sensor I will use here. Okay, and we have the robot itself. This is the robot. So the information I want to know, the LiDAR readings itself, how many meters away from the walls, where are the obstacles exactly, and also we need the information about what is the distance that the robot is displacing from a point to another. So we can get this information from the ODOM. This one, this topic ODOM. The ODOM is saying the information from the encoder, from the incremental encoder in the wheels itself. Okay, and we also know the transformation of the frames. We have a frame in the center of mass of the robot, and we have another frame maybe for the LiDAR itself. It's fixed frame. If the robot is moving, the LiDAR will move with it. So it's fixed frame. So this distance between these two frames, or the transformation matrix between these two frames, are published or are displayed in this topic called TF static. Okay, and for the robotic arm, maybe for the robotic arm, for the end effector, maybe if you are moving with the robot and the end effector is moving somehow to another location, so now the frame of the end effector is dynamic, not static. It's dynamic relative to the robot. So we are publishing this message also on the TF, on the topic TF. Okay, and then integrating all this information to do a SLAM, simultaneous localization and mapping. Okay, so we are building the map while at the same time knowing our location or estimating our location in the map. Okay, then to make sure of our location in the map, we are using something called AMCL, Adaptive Monte Carlo Localization. It's using EKF, Extended Kalman Filter, in order to make sure about the location exactly of the robot. Then we are going to the navigation. This is the final step. The navigation, that we are putting a goal pose to the robot, and the robot already know the initial pose of it, so it can plan a way that we can go to the goal. Okay, and this way is planned according to this artificial potential feed. So I know the goal, I know the initial pose, how I can go to it if I have an obstacle in the middle. So I have maybe I have to rotate like this, or maybe I have to rotate like this in order to avoid hitting this obstacle. Okay, using this artificial potential field. And yeah, I think that's all. In the middle, you will have some issues like what we faced today, like user input. From the user input, you can initialize the pose. You can estimating the pose in order to calibrate its position relative in the map, inside the map.
I have one last question.
Yeah.
Did you write all of the SLAM and all of the localization algorithms yourself?
It's only modules. It's already online. The SLAM itself, it's a node. It's a node like a human, making some calculations and sending a message, hearing messages like scan, ODOM, TF static, hearing these messages and make calculations and publish another message that's like the map, the location of the robot and all of this stuff.
But
So it's already built.
Connecting all of these nodes, you did it, right?
Yeah.
So and how did you do it?
Through ROS.
Through us.
Yeah.
So the most important, if you want to work in robotics, as a software engineer in robotics, the most important skill is ROS. Go learn it, tutorials, take courses online or whatever. Learn it, and then you will be able to use other people's work and connect them to your application. So this is really the most important.
I have a question.
Yeah.
So SLAM node, does it like already like the type of sensors are being identified inside it? And he knows that.
Configure.
Yeah, so I would, okay, I have a LiDAR, I have this LiDAR. Okay, what about sensor that, or a thing that is not, could be used as sensor, like Wi-Fi signals?
Another SLAM algorithm.
So I have to,
Another SLAM. You have to look for it.
so I have to configure it from the,
You have to look for it. Maybe this one is, it's an algorithm that uses LiDAR, IMU, and GPS. But you want to add on it the camera. So you need to look for another algorithm that does it. Or maybe you think of exactly like using thermal camera to do stuff. Or I want to use magnetic sensor to do this. Depending on the algorithm. If someone else did it, you're happy.
if
And
not,
it's available in us. If not,
I have to do it myself.
you have to do it. How?
I have to model the sensor.
You have to, no, not just buy the sensor. You have to build the EKF itself.
Yeah.
All of what we discussed for many years. And that's the most difficult part. So you build the EKF, you build the state transition model and the measurements model, you identify all of the stuff, you tune the gains of the filter, and then you just let it run. And that's exactly the result. And then you go to the real robot and see whether it's satisfied. Okay? Thanks a lot. Did you enjoy, guys?
Yes.
Can you thank Tarek?
Yeah,
He really did a great job. Okay. It's not that hard to do an online demo. It's really difficult.
Yeah.
No matter how well you're prepared, it will always fail. Jazakallah khair, Tarek.
Thank you. Thank you so much. Thank you so much.
Yeah. That's it. Jazakallah khair.